I'm a knot theorist, so let's start with very basic definitions. So, a knot is an embedding of a circle into the 3-sphere, and we say two knots are equivalent if they are isotopic. Similarly, a link is an embedding of circles into S3. So we say two links are equivalent if they are isotopic. So these pictures are examples. The first one is right-handed trifold knot, and the second link is called the Borromean ring. Okay. So we can represent a knot or a link by projection to xy plane. So and this is a famous theorem by Reidemeister. So let's say K and K prime be two links, and D and D prime be diagrams for each K and K prime. So then K and K prime are equivalent if and only if it is possible to transform D into D prime by the following the sequence of the following three local moves: R1 and R2 and R3. So this theorem gives a combinatorial way to do that theory. So for example, if we define something that depends on the diagram, and suppose that we want to show that this is an invariant of a knot or a link, then it is enough to show that that invariant is actually invariant under these three moves. And for a given knot K, the unknotting number UK of K is defined by a minimal number of crossing changes to transform K into the unknot. So for example, this is a triple knot, and if we change this crossing like this, then it became a unknot. So this is another example. If we change these three crossings, then you can check that this is isotopic to this original circle. So we can say that the unknotting number is that at most 1 in this case and at most 3 in this case. So it is typical way to define a knot invariant by taking some minimal value of something interest. For example, the crossing number of knot K is defined minimal number of crossings in all possible diagrams of K. And the important invariant, the 3 genus of K is defined by a minimal genus of surface in surface F in S3, which bounds the given knot. So, and there are so many invariants like smooth four genus or bridge numbers, dot, dot, dot. In many cases, we can give an upper bound by showing on explicit example, like this case. But however, giving lower bound is not easy in general. So in this talk, we will see one way to give a low bound for unknotting number by using so-called Khovanov homology. Okay, now let's move on the symmetric version. So a strongly invertible knot K is the knot K with an orientation preserving involution tau on 3-sphere such that tau K is equal to RK. So here RK means the reverse of K, which is a knot with same image, but just orientation is reversed. And we say that two strongly invertible knots are equivalent if there is an isotopy which respects the symmetry. So here are examples. If we consider a 180-degree rotation on this axis, then this right-hand trefoil, the image of this right-hand trefoil is just preserved, and the orientation is reversed. And the right one is a figure 8 knot, and you can easily check that this is also strongly invertible. And one thing I want to note that is that there is a two fixed point on the axis of the knot here. Then we can consider a symmetric version of the unknotting number. So Boyle and Chen considered these three types of equivalent crossing change. The type A crossing change is the case when two symmetric crossing change happens off the axis. So there are two crossing changes. And type B and type C are when the crossing changes happens on the axis, but the type C crossing change is about when these two fixed points collide, like this movie. So they are slightly different. And now the equivalent unknotting number is defined in this following natural way. So we say that equivalent unknotting number to be minimum number of such that K can be unknotted by UA times over type A crossing change and UB times of type B crossing change, UC times of type C crossing change, then take a minimum number of 2 UA plus 2, I'm sorry, 2 UA plus UB plus UC. So it is natural to put the coefficient 2 here because we have two crossing change here. So why do we consider the equivalent setting? So first, the equivalent setting is itself is interesting than the original setting. So the one case is about the concordance group. I will explain briefly. So we say two knots K and J are concordant if they are smooth embedding of annulus into the S3 times I, which bounds given knot K and J. So it's like it looks like this K, and here is a concordism. So in this case, we say that K and J are concordant. So not modulo this relation form an abelian group is a connected sum operation. So most of knot theorists are interested in the structure of the concordance group, and uh, we can also define the equivalent concordance group by using analogous definition for strong invertible knots. But interestingly, Frisa showed that the equivalent concordance group C tilde is even not abelian. And the second example is that the usual unknotting number satisfies this inequality. It is quite obvious because if we want to make K1 connected sum, K2 be unknot, then we just make this part as an unknot and this part as an unknot. So yes, so this inequality is quite obvious, but Boyle and Chen showed that the equivalent unknotting number does not satisfy this inequality in general. Actually, they showed the example. They found the example that u tilde of K1 connected from K2 is strictly greater than u tilde of K1 plus u tilde over K2. So interesting things are happening in equivalent setting. And it has an application to find some exotic phenomenon. So these three mathematicians find some specific strong invertible knot K with a slice disk T. So let's say this is a specific knot K, and there is a slice disk T. And then by the involution tau, it has another slice disk coding in the forward, then they showed that these two slice disks are topologically isotopic, but not isotopic in smooth sense. Yeah. Now let me introduce the tool what I used. This is called Khovanov homology. So for a given link diagram T, we assign a chain complex KHD. This is a chain complex over F2H modules, and it has a bigrade structure. So it has a homological grading and quantum grading, but we don't consider this bigrading today. And it is constructed in combinatorial way. So there are some of computer programs to compute the Khovanov homology of the knot or links. Actually, of course, this gives an invariant for knot or a link. So due to the following theorem. So suppose we have a two diagrams for a link, given link K. Then these two chain complexes are actually chain homotopy equivalent. So its chain homotopy type or the homology, which is denoted by Khovanov homology, are invariants for link K. So proof idea is that for each Reidemeister movement, R1, R2, and R3, we can construct a chain homotopy equivalence from one chain complex to the other one. Then the proof is done by previous Reidemeister theorem.
Sorry to interrupt, Kee Taek, but there's a question in the chat which seems fairly. So the question is, how can we define the map in the definition of a strongly invertible knot on the connected sum of two knots? And you can probably.
Yes, that's a little bit subtle definition. So actually, if we want to define the connected sum between two strong invertible knots, we need additional notions like direction. So for example, we have so this is let's say this is an axis, and suppose we have two strong invertible knots. Oops. Oh, I get into the but then as I said before, we have two fixed points for each knot, and we need to choose one fixed point for each knot, and we can then we can connect them like in this way. So it became a connected sum of the given two strong invertible knots. Okay. Yeah, thanks for the question. Yes, so this is a well-defined invariant for knot or a link. So and let me briefly introduce the construction. But I'm not going into details. So given link diagram T, and then we first get a so-called cube of resolution. Then we can take a appropriate TQFT on this. Then we get a chain complex of modules. Then take a homology. So finally we get Khovanov homology. So let's see an example of the trefoil. So this is a diagram, and we have three crossings here. And there are two ways to resolve each crossing, like this way and this way. So because we have three crossings, there are total 8 possibilities, and we want to record these all of 8 diagrams like this complex. So this process is so-called cube of resolution, and each arrow can be considered as a cobordism, like pencil picture. So for example, this arrow is corresponds to the splitting cobordism like this, because we have one circle here, but it divides into these two parts. Yes. Again, I'm not going into details, but I want to remark that if we concentrate one specific crossing like here, then this cube of resolution can be considered as two parts, this and this. So the red part is about where the this crossing is smoothed like in this way, and this blue part is about this way. So the whole complex is a combination of each complex, and there are arrows from this red part to this blue part. Then we can apply TQFT on the cube of resolution. So TQFT is simply we assign module V on each circle, and each cobordism gives maps between it gives maps between modules. So uh, there are several ways. So for example, here are two circles. So it corresponds to V tensor V and so on. So there are several stars at here, but this is for the technical reason. So please ignore it at this point. So this is a chain complex of modules. So like this is a homological degree 0 part, and this is a homological degree 1 part, and so on. Then finally, we can take the homology. So the result is here. So the Khovanov homology of the right-hand trefoil consists of this one free part and this torsion part. So as the previous example, for a knot K, Khovanov homology consists of one free FTH part at homological gradient 0, and other parts are just H torsion parts. So in this talk, we are interested in the torsion part. So let's define torsion order as a maximal H torsion order, and shortly we will write word K for torsion order of the Khovanov homology of the given knot K. So for example, this knot has this table of Khovanov homology, and this is one free part, and there are two torsion parts, and here we have a torsion order 2 here. So the torsion order of this knot is equal to 2. Ah, I should remark that technically this in this talk this should be called by reduced. I'm sorry, reduced by atom homology. But please forgive me for just call as a Khovanov homology in this talk. Okay, then let's consider the equivalent sense of the Khovanov homology. So for given strongly invertible knot and its strongly invertible diagram, then the involution tau on S3 induces an involution on the chain complex. For example, if we draw a triple like this, then the involution gives an involution on chain complex like this is left to this part, and this goes into it itself. So for strong invertible knots, we have more information that not just only the chain complex, but together with an involution on the chain complex. So we can record this involution on chain complex by mapping one as following. So let's call this as an involutive Khovanov chain complex. And this is a theorem by Taketo Sano. So if we have a two involutive diagram for given strong invertible knot, then these involutive Khovanov chain complexes are chain homotopy equivalent. So each chain homotopy type and homology are invariant for strong invertible knot. Okay. So similar to Khovanov homology, the involutive Khovanov homology consists of two free parts at homological reading 0 and 1 for each, and other parts are H torsion parts. So let's define the equivalent torsion order as the torsion order of the involutive Khovanov homology. And this is an example. This knot is same knot with the previous example here, but in this diagram, it is drawn in the symmetric way. So this knot with this specific involution count, we can compute the involutive Khovanov homology, and the table looks like this. And for this case, again, we get the torsion order 2 from here. So now I can talk about the low bound for the unknotting number. The original work is done by Alishai. So suppose a knot J can be obtained from a knot K by one crossing change. Then there are chain maps between two Khovanov chain complexes F and G such that their compositions are chain homotopy to H times identity. So the idea is that, as I said before, if we concentrate one crossing, then the whole complex divided into the two parts. And if we change crossing this into this, then the role of this red part and blue parts are changed. So if we change the crossing, then the whole chain complex looks like this blue part goes to this red part like this. So Alishai defined appropriate maps between this to this and this to this and vice versa. So and checked that this map actually satisfies this homotopy relation. Then this is a purely algebraic lemma. So for chain complexes C and C prime of FTH borders, such that they have a chain map F and G, which satisfies these relations, then the difference of the torsion order is bounded by K, which comes from here. Then this corollary is immediate because for each one crossing change, we have a 1H here. And if we need n crossing change, but then we have a h to the n in final stage, so we can bound the unknotting number by the torsion order of k. Of course, the order of the unknotting number is 0, so it works. No, I'm sorry, but so okay. Okay, let's move on the equivalent side. So this proposition is just extension of the Alishai's theorem. So if we have a strong invertible knot J, which is obtained from knot K by type A or B or C crossing change, then the similar things holds for the involutive Khovanov chain complex, but in this case, K should be 2 for type A crossing change, and K can be 1 for type B or C crossing change. So by the same reason, the similar corollary holds for the equivalent side. So these maps F tilde and G tilde are based on the Alishai's maps, but we need to prove that the homotopy between GF and H times identity is well behaved under the involution power on the chain complex. So then we can extend these maps to mapping cone. So let me just skip this slide for time. So let me finish my talk with a small example. So this is not 7 in of sense knot table, and this is the table of the Khovanov homology, and you can easily check that here is the free part and others are all torsion parts with torsion order 1. So it has a torsion order 1, and this knot is looks like strongly invertible. So with this involution, the involutive Khovanov homology of this strongly invertible knot has a torsion 2 at here. So its equivalent torsion order is equal to 2. That means we need at least two equivalent crossing chains to make this strong invertible knot into the knot. So actually, these pictures illustrate how we transform this knot into the knot. So in the usual sense, if we change this crossing, then you can check that this is the knot, but as we complete the equivalent torsion order, it cannot be done by one equivalent crossing change. But if we do two equivalent crossing change, like this way, then we have an unknot. So its unknotting number is equal to 1, but its equivalent unknotting number is not 1, but it is 2. Okay, this is the end of my talk. Thank you for listening.